All right, let's go ahead and talk through some of the information needed to complete Lab 7. So with this one, we're looking at densities. The main formula that we see for density is that it's mass divided by volume. Technically, density can be any mass and volume combination. It can even be weight compared to volume in some cases. So we can use several different combinations of units and they're all technically acceptable. So in the standard units, we might see something like pounds per gallon or pounds per cubic foot. In the metric system, we would typically see something like grams per milliliter, grams per cubic centimeter. We want to remember that those are actually the same as each other. Or gases, because a lot of times they're very low density, we might see grams per liter. It just kind of depends on how dense they are, how they're concentrated. Okay, so we have three different parts to this lab that we have to pay attention to. We want to find the density of a sample of water. The water is a little bit difficult to measure, and honestly, the water from the lab's not super clean because I don't run water through the pipes all that often. So we definitely wouldn't want to drink it, but it is at least safe enough to do the lab. So we have to carefully take some measurements from there. Then we have a black rubber stopper, which is a little bit of a weird shape. So it'd be something like kind of like a rounded wedge or maybe a cone with the end cut off. And because it's a weird shape, we have a little bit of a challenge in finding the volume. So we have a way that we can kind of work backwards and do that. And then finally, we have a almost a cube, basically a metal block that we'll find the density of, and then use that information to guess what type of block it must have been. Okay, so we have a procedure here. We To find the density of the water, we first have to find the mass and the volume of the water. And so, you can pause and read through that part, but I have some numbers ready that we can use to go through and calculate here. So the mass of the cylinder that I had was 124.34 grams. And then when I filled that full of water, got 197.28 grams. So we can't find the mass of the water directly because if we tried to pour it on the graduated cylinder, or sorry, pour it on the triple beam balance, then obviously it would spill everywhere and make a mess. So what we have to do is we have to find the mass of a cylinder when it's clean, dry, and empty. Then we fill it with water and then use that to find the difference. So that's why it may seem a little bit weird with the order on these, but basically it was designed so that you could subtract these right in line and get an answer. So the mass of the water that we're looking at would be 72.94 grams. Now, the volume of the liquid you can read directly from the graduated cylinder itself. So water in a graduated cylinder makes a dip. So it has a concave shape and something called a meniscus. So water has high adhesive forces, and so the water sticks to the sides of the graduated cylinder. Sorry, my line kind of missed. And so when you see that, the water kind of climbs up the sides a little bit, and what we do is we read the bottom of that meniscus. And then with the way the lines are set up on the graduated cylinder, we can read one decimal place. So for my example here, we had 73.6 milliliters that we could read off of the graduated cylinder. Okay, so then to find the density, remember we had that formula from earlier that density is mass divided by volume. So for our particular numbers that we worked out from here, that density is going to be 72.94 grams divided by the volume, which is 73.6 milliliters. So we can see the grams per milliliter here for the units that matches what we're looking at. Then dividing these two numbers out, we get about 0.991. All right, so specific gravity then, the hints are on here, unfortunately, sometimes confuse students. So number 3 divided by number 4 means the answers to questions 3 and 4. So we have those hints here, and again, it matches our formula. But this is number 5, literally divided by the number 1, because specific gravity, what it does and how it works is it takes the density of some material and it compares it to the density of water. And by putting those in a ratio and dividing them out, then we're going to get typically some decimal number from this. And so what's going to happen is we found the density of our material, or our liquid substance here, and we got 0.991 grams per milliliter. So pure perfect water, if we can take perfect measurements, is 1.0 gram per milliliter. So water is one of those things, kind of works as a definition for a lot of stuff. So we literally divide by the number 1, like the value 1. So that's why there's not a symbol in front. We're not dividing back by this thing at the top, but we're literally just dividing by the value of 1. The units are going to cancel from this because they match each other. And then what happens is we actually get the same number answer for questions 5 and 6. But the specific gravity just drops the units off because of how we divide to find that. Okay. And so that's how we would work through our first setup and procedure. So for the second one, for the rubber stopper, it's a little bit of a weird shape, but this time it is a solid shape. So it's an object that will hold its form, and so we can put it just directly on the triple beam balance this time. And so the mass of one of these things, they change depending on the size of the stopper, but the one I was looking at was 15.64 grams. Now, unfortunately, the stopper itself, because it is kind of a weird shape, it would be very difficult to try to stick a ruler to it and take measurements and calculate a volume. There is a way to do it if you measure enough different parts. You could either look at it as like a trapezoid that's been rotated, or you can look at it as like a cone where the tip has been cut off. And technically you could find the volume of the full cone and then subtract the part that's been cut off, but it just seems really complicated. And so we have this procedure that we can use where we can work backwards a little bit and determine the volume of the stopper anyway. So our initial reading of the water in the graduated cylinder is going to be the same as what we had from earlier. So we would still have 73.6 milliliters of water in our cylinder. Then we put the stopper in there gently so that it doesn't splash and get water stuck to the side of the cylinder. But then we put the stopper in there, and it causes the water level to rise. And so the amount that the water level goes up is actually the size of the stopper itself. So the amount that it displaces water is the displacement or the size that it has, and we can use that to our advantage. Okay, so the water level goes up to 85.9 milliliters. So the volume of the object is going to be the difference between those, and so we subtract them and get 12.3 milliliters. Okay, and now we actually have enough information that we can find the mass density. So remember once more, that mass density takes mass and divides by volume. So if we look at our values from this, our mass is 15.64 grams. Our volume, remember, is the difference in those readings, and that's 12.3 milliliters. So dividing these units is going to give us the grams per milliliter, so that's good. And then calculating that value, we get 1.27. Then remember again, specific gravity is going to take that density and divide by the value 1. So, I hope you can see where this is going, but we're going to have that density. The density of water is 1.00 by definition, grams per milliliter. So we get the number back, but the units are gone. Okay, then the regular solid. So, and then eventually we want to guess what type. So the regular solid basically just means that it's an easy shape to look at, is almost a cube, but not quite. It's just a metal block. I guess it would technically be a rectangular prism. And we're supposed to stick a ruler to it, but I suppose I broke my own rules. I used a caliper instead. So I have an extra decimal place on my measurements compared to what you can get from a ruler. But I found that the block was 3.127 centimeters in one direction by 3.164 centimeters in another direction and 3.089 centimeters in the other direction. And, typically we think length, width, and height in that order when we're thinking of volume of a boxy sort of shape. Those are kind of arbitrary because you could lay the box on its side or flip it over a different way, and then those all kind of scramble. But as long as we have the three different measurements, then that's enough information for us to find the volume. Now, you might kind of see something going on here that's a little bit confusing. We've got all these different centimeters, and so if we multiply those together as they are, we get centimeters cubed, right? Because there's three separate measurements of centimeters. Multiplying those particular numbers together, we get 30.56. Again, an extra decimal place compared to what you would get from a ruler, but that's not going to overall hurt things too much here. The question wants milliliters, though. And so minor typo in the way that showed up. Typically milliliters has the capital L, but I suppose it's not that big of a deal. But there was a clue from early on in the lab in the beginning information. Cubic centimeters are also sometimes called cc's. And cc's by definition are the same thing as milliliters. So it's free. It's not even really a conversion here, but by definition, these things are the same. You may have come across this before if you've ever had to measure out liquid medicine for a small child or for a pet. So sometimes you'll have a syringe that measures out in cc's, or sometimes you use a little cup that measures out in milliliters. But like I said, those are the same. So that's nice. We don't actually do any work. We get kind of a free answer on that part. The mass of the block, because again, it's a regular, easy sort of shape. It's something that's solid and will hold its form, can just go straight on the triple beam balance. And what I have recorded from before is 83.43 grams. Okay, and that's perfect. Plenty of information here. So we go ahead and find this density, same way we have before. So density for mass density just has a mass on top divided by a volume. All right, so for our value, 83.43 grams divided by the volume that we had to calculate, we've got 30.56 milliliters. And so that's going to divide out and give grams per milliliter, which again is good news. Then that's going to give us about 2.73. It's reasonably close. I've trimmed a decimal place here because technically we should have had one fewer decimal places on that part, but that's not going to be super picky on this one. The specific gravity, we've already seen this work a few times, but the hint's not here this time, I suppose, so I guess I'll work it out and help. But we've got 2.73 grams per milliliter for our calculated density. Remember, we compare it to the density of water. So that's 1.00 grams per milliliter there. So it cancels out the units and just gives us the number back here. All right, and then the final thing we want to try to do is we want to use this information and try to see what kind of a block we were dealing with. So from the textbook, we have a table of values, and as it turns out, aluminum is the first one, 2.7 compared to 2.73, seems pretty close. Some other things we might have had, brass is 8.44, so that's considerably larger. Definitely don't have any gold, but if we did, it would have a much higher density than the 2.7 we were looking at. There are iron and steel blocks, and those are in the 7 to 8 range, closer to 8. So again, that doesn't match. I do have lead blocks, so that's between 11 and 13, depending on where you look up the value. And again, that's very much higher than what we found. So 2.7 is by far the closest value, and that would be aluminum. And there we go.